Okay, welcome back to astronomy. Let's talk about the Earth, Moon, and sky. On the surface of the Earth, we can define the location of a city quantitatively using two numbers. One of them is with longitude, and the other one is latitude. Latitude is measured with respect to the Earth's equator. Longitude has a reference point, which is this great circle, which is called the prime meridian, and that's where you start measuring longitude from, and it goes through the city of Greenwich, England. Similarly, on the celestial sphere, we have coordinates declination and right ascension. So declination is similar to latitude in that it's measured above and below the equator, the celestial equator in this case. And similar to longitude, we have right ascension measured with respect to this great circle defined by the vernal equinox. So it goes all the way around here to measure the right ascension. So the vernal equinox is used as a reference for right ascension. Greenwich, England defines the prime meridian, defines that great circle. If you go to Greenwich, England, you actually will see markers on the ground indicating that that's where 0 degrees latitude starts. Seasons, as you know, are caused by the tilt of the Earth's axis. As we go through the seasons, we see that on the first day of summer for the northern hemisphere, rather, in the southern hemisphere, it's winter time. And then we go over here to, we're going the wrong direction. Summer, let's go over here to autumn, is the first day of fall here. And there's equal amounts of daylight and darkness on this day. 12 hours of daylight, 12 hours of darkness, equal nights, equinox. And then over here, we reach the winter solstice. It's cool for us. It's winter time for us, but in the southern hemisphere, it's actually summer on December 21st. So in the southern hemisphere, the seasons are reversed. And here we get the first day of spring, also called the vernal equinox, on March 21st. You can see why it is that in the summertime, you have warmer weather, because if you look at a square meter of light, and if the sun is off in this direction, it's spread out over this area here, let's say 1.04 square meters. But in the winter time, you get much more spreading out of that light, and so you get less, power from the sun there, or I guess watts per square meter is going to be lower. So that's the reason why it would be feeling cooler. If we look at the path of the sun for mid-range latitudes, and that's the case for all three of these, let's suppose this is a person in Nacogdoches. The sun on the day of the summer solstice, it takes it high in the sky. The sun would rise north of east and set north of west. On the day of the equinox, however, in Nacogdoches, the sun rises due east, it goes and crosses the meridian and then sets due west. And finally, on the first day of winter, it rises south of east and sets south of west. Here's some additional graphics talking about how sunlight gets spread out here. This is on June 21st, the first day of summer. And they indicate these different regions like the Tropic of Cancer. And you can see that the Tropic of Cancer goes just above Cuba there, just below Brownsville, Texas, right in that area. And that has a latitude of 23.5 degrees right there, which means if you're on that particular latitude, the sun will be directly over your head on the first day of summer. You'll notice that in Texas over here, the sun never really gets to the point directly over your head. And you have a similar situation here in the southern hemisphere with this other line called the Tropic of Capricorn. On the other hand, in December, on December 21st, the winter solstice, we have the same kind of situation happening here. The people that live here on a latitude of 23.5 degrees south of the equator would have the sun directly overhead on this particular day. If you go further north in this, you can never really get the sun directly over your head. And of course, if you get to this point right here, you're seeing the sun all day long, but it never reaches the point directly overhead, of course. The difference between the so-called sidereal day and solar day can be best represented by this diagram Imagine you have a situation where you have a line joining the sun and the earth. There's a person standing on that line. And as the earth spins, it also orbits in this direction. Now, what's not shown is an imaginary situation where you have the person standing right here on this line right there. At that point, you would see the same star. If you pointed off in that direction, there would be a star in that direction. That would be the same star that if you pointed into the sky, you'd be pointing at the same star very, very far away. And so that's the time with respect to the stars. And that is referred to as sidereal day. So sidereal day is the time with respect to the stars. You have to go a little bit further until the sun is directly over your head, and that's called the solar day. So there's a 4-minute difference between those two. And for each day, you basically have the sun moving 1 degree, I'm sorry, the earth moving 1 degree around its orbit, and it makes it look like the sun is moving 1 degree across the celestial sphere. We've talked about Greenwich, England being over here. If you look 180 degrees away from that in longitude, you can see that what we have done as humans has defined this place out there in the water where this is called the international dateline, so that two neighbors won't be, on different days. So this international dateline was carefully planned out so that it helps communities and countries work together without having to be in different days. The next part we're going to talk about is objects in the sky that serve as a calendar for our computers and our wall calendars and things like that. When we look up into the night sky and see bright objects that wander around, there are a few of them that come to be obvious, and we'll call them naked eye solar system objects. Now, the first thing that's obvious that you can see with your naked eye that moves with respect to the celestial sphere is the sun, and then obviously the moon as well. Other things that wander across the night sky are Mars, Mercury, Jupiter, Venus, and Saturn. Now we're talking about naked eye objects. So we're not going to include the Earth on this because we're on the Earth viewing the night sky. And we're not going to include Uranus, Neptune, and Pluto, or comets and asteroids, because you can't see those with your naked eye for the most part. You have to use a telescope to see them. These are always around. These 7 objects are always around, and if you have a clear sky, you can eventually see them during a period of a year. And it turns out that these 7 objects are what gave us the names of the days of the week. So Sunday, Monday, Tuesday, Wednesday, Thursday, and Friday, and Saturn Day here all have their origins from these celestial objects. You might see this in other languages. I think I have some other languages up here: English, French, and Spanish. Let's look at a couple of them here. Like for this one, for Mars, and let's see, Tuesday. Let's see, that was not so obvious where it comes from here. Thursday, that seems to be a little bit more obvious, and obviously the Saturn one is an easy connection. But I wanted you to note that the days of the 7 days of the week come from the sun, the moon, and the visible planets that you can see with your naked eye. So if you were to look at these planets, even in ancient times, Mercury is difficult to see, but if you look close to the sun, you can see it, and it will not be, it'll be obvious that it's not part of a constellation, and it wanders around the sky as well. Venus is a very bright object. It's the 3rd brightest thing in the sky. The sun and the moon, and then Venus is 3rd place as far as brightness. We often refer to Venus as the evening star. Mars is noticeably red. It can be very far away from the sun, in fact, in an opposition configuration. Jupiter and Saturn are also bright or moderately bright, easy to see with your naked eye. The sky is a calendar, and we've learned already in this course that a day is basically the time for the Earth to spin about its axis once. A year is a time for the Earth to orbit once around the sun. And then what might be new to you is the word month. That is the approximate time it takes for the moon to go around the Earth. So moon and month kind of have the same origin. So our calendars, the days of the week, even the time has astronomical origins. Another example is the number 360 degrees. Why do we use that for one circle instead of 100 degrees or something more obvious? And the answer to that is it takes about 365 days for the Earth to go all the way around the sun. And Greeks like the number 360 better because it was evenly divisible by 2 and 10 and 15 and 4. It's just a nice round number that can be broken up into nice integers. And so for that reason, we use 360 degrees. Some astronomers thought that it was really 360 degrees. In other words, the Earth moving 1 degree per day around its orbit. One of the things that we've discussed here as far as the sky dome is concerned is the location of where the sun rises and sets. And so on the day of the equinox, we would notice that it would rise due east and set due west. On the day of the winter solstice, it would rise south of east and set south of west. And then on the day of the summer solstice, it rises north of east and sets north of west. See, it didn't quite get to the zenith here in Nacogdoches. If you look at the starting points for all three of those, you can see that this one's due east. This one turns out to be 23.5 degrees toward the south. This is 23.5 degrees toward the north. And we, of course, are not the first ones to notice this kind of thing. We can see many examples of cultures in which they notice the special locations of the sun during the year. Some among the Anasazi people carved a spiral into this because they noticed that this sliver of light would go right through that, they would appear right there on that flat surface. This is the so-called sun dagger on a vertical cliff face in New Mexico. So there the sun's rays form a dagger, and I think it occurs, the first day of summer. So you can only see this sliver of light one day out of the year. Kind of a rare event. So when you look at the research on Stonehenge, you also find that it serves as kind of a sky calendar. You can stand at various locations at Stonehenge and witness certain events such as the winter solstice, the winter sunrise, and then there's one location, I think you're standing here, looking off in that direction at the Heelstone. Do I have a picture of that? I think I have it on the next slide. So on a certain day of the year, you can see that the sun is just right there at the top of that stone, that so-called Heelstone at Stonehenge. So it's thought that Stonehenge was basically a calendar, and we find evidence of other cultures and societies using structures to try to keep track of the seasons and the years, such as in this case in Wyoming of a bighorn medicine wheel. Later on in this chapter, we begin to talk about the phases of the moon. We'll have a lab associated with the phases of the moon. And simply put, what we can do is go over here and start at this location here where we refer to the moon as being new. We can see that if we're on the Earth looking this direction, it's in complete darkness. Here we see a sliver of light, so waxing crescent. Here we see half lit up, first quarter. Here we see it mostly lit up, because it gives us more light. And it's waxing, that's increasing the amount of light. Eventually we're seeing the entire illuminated surface of the moon, making it full, and then it begins to wane as we go to waning gibbous, third quarter, waning crescent, and then back to new again. And that takes 1 month for the moon to go through all of those 8 phases. Another thing to note about the moon's rotation that you may have noticed when you look at the moon is we only see one face of the moon. To some it looks like a rabbit, like this is the body of the rabbit, the head and the ears. Some people see like the man on the moon, like face on the moon. And it's always going to be facing toward the Earth because the spin rotation of the moon is about a month and the orbit rotation is about a month. And they're they're locked in. It's tidally locked so that you always have one face of the moon facing toward the Earth. So this is the familiar face of the moon, and this is the far side of the moon that we never see. So this had to be imaged with the Apollo astronaut missions, as well as unmanned spacecraft as well. And you can see it has a lot more craters, and on the near side, we see the dark areas called mare, which is like frozen volcanic material, so solidified volcanic lava. The moon is responsible for the tides on the Earth. And you can see if you look at the gravitational pull on this side of the moon, since it is closer, this vector is longer, and the gravitational pull on this side of the Earth from the moon is weaker, hence the shorter vector. So the net result is kind of a stretching of the Earth's oceans, the so-called tidal effect. So in this case, this is an exaggerated case, of course. We have the so-called tidal bulge, this light blue representing the Earth's oceans. And so really, when you talk about high tides and low tides, it's you rotating into the bulge of the water. So it's not really, I guess, the water rushing up. It's really you're going through the higher portion of the bulge of the Earth's oceans. And of course, we can see clear examples of that if we live near the coast of high tide and low tide. So the moon is responsible, or primarily responsible, for the tides on the Earth. The sun plays a secondary role. If you have the sun and the moon lined up like this, you'll get extra large tides, and that's called a spring tide. And then the moon kind of dominates here. If it's 90 degrees between the moon and the sun, then the sun kind of lowers the high tide, so to speak. And so you get a lower high tide, and this is referred to as a neap tide, when the sun kind of cancels out some of the effects of lunar tides. The later part of this chapter talks about eclipses, and anytime you have a light source with an opaque object in front of it like the Earth, it's going to cast a shadow out into space. It has a darker part of the shadow and a lighter part of the shadow. In fact, any time you cast a shadow, if you look closely at the edge, you'll see kind of a fuzziness to it. That's the penumbra out here, and this is the darker part, the umbra. So in this case, if we're at position 1, we don't see the sun at all. If we're at position 2, we see a partial eclipse of the sun from the Earth. If we're at position 3, we see more of the sun than we saw at position 2. And if we're at position 4, we can actually see a little bit around the Earth, and we can see a little bit of the surface of the sun. And this kind of eclipse is referred to as an annular eclipse. This is called the annulus around the outside. So this would be more like a total solar eclipse. This would be an annular total solar eclipse. So this one, I guess, would be a total, total solar eclipse there. Lunar eclipse, on the other hand, happens not when the moon is over on this side, but instead back over that way. And it's not really dangerous for you to look at a lunar eclipse because you're looking at the moon and the sun is all the way on the other side of the Earth. So it's not dangerous to look at a lunar eclipse because you're just looking at the moon going through this Earth's shadow. So you can kind of imagine the Earth's shadow, and those are 3 different pictures of the moon as it enters the umbra, gets into the umbra, and then refraction around the Earth's atmosphere gives you the reddish color there, and then it exits the umbra over here. Solar eclipse can be either total or annular depending on how far away the moon is from the Earth, because it's not a circular orbit. The moon's in a slightly elliptic orbit around the Earth, so you don't always get a total eclipse. But if you get it just right, you can get this dark shadow creeping across the surface of the Earth, and if you happen to be in that shadow, then you'll see a total solar eclipse. And they're quite amazing to look at. I saw one in 2017. Had to drive all the way to the Path of Totality in Missouri to be able to get this kind of view. There's going to be another solar eclipse where the path of totality is coming through Tyler, Texas in 2024. So be sure to look me up around then, and we'll get a nice view of this solar eclipse coming soon to a city near us. All right, that's all for now. I'll check back in with you all later.